All right, well, welcome to another lovely Friday here in Math 202. Before we keep on our discussion about, well, where we're heading now is to start talking about motion of objects and using the big N's and the big T's and curvature and all that good stuff that we figured out so far. But before we dive back into that, are there any questions from the homework? Anything out there or from the last couple of classes that we want to chat about?
Yeah, I have a question.
Sure.
So if you wanted to find curvature of, say, a road, we'd use that circle of best fit or some function to mold to it.
Probably what you would do. Well, all right. So are we going to assume that this road is pretty much two-dimensional, or
Yeah, we
goes
could make that
3D?
assumption.
Okay, so if it's pretty much two-dimensional, which, and as long as we're not cruising through the mountains, that might be reasonable. What you would probably want to do is plot a couple of points relative to each other, right? So go out, create a coordinate system somewhere, and then get some points along that road. And then what you'd want to do is probably figure out a curve that fits it. Now that's going to really kind of depend. Obviously, the more points you have, the more you're going to be able to determine a curve that fits it pretty well, right? If you only have 2 or 3 points, then it could be just about anything. So you'd want to get a series of those points, figure out a curve of best fit. If it's two-dimensional, probably the easiest would be is if you could write it as y equals f of x, and then use that last, the fourth of the formulas that we had for curvature. So that would probably be the attempt. Now, obviously, it's going to depend on how good you are at creating a function that fits those data points. And what you might even have to do if you had like a larger road, like let's say you even had a pretty decent map of the road, someone's already gone and done the surveying and all that. So you've got a decent map. You might want to break it into pieces and basically have a whole bunch of functions of best fit, so that you could find the local curvature at different locations. In an applied setting, I think you'd be more concerned about the curvature at just some specific points, maybe those tightest of turns and all that, because that might help you determine how much you need to bank the road, what kind of speed limit to put on it and all that. And so it might not be that challenging because you could really localize it. But that would be the process I would try to do. But again, remember, I'm not a civil engineer, so they might have all kinds of lovely techniques for actually calculating it, if it's something that they are really concerned about. So, and that's the other thing, is they may not be concerned about curvature as the number as we're defining it, but the concept they are going to be concerned about, for things like I talked about, the construction of the banking of the roads and things like that.
Okay.
Cool. Other questions? I know Bradley's always good for something that's a little off the wall, but not really. It's still related to what we're doing. So I always appreciate that.
Thank you.
All right. All right. Well, then let me go ahead and switch cameras and head on over to the whiteboard. So I will see you guys in just 1 second. All right. So what we're going to do today is we're really going to start using this stuff. We're going to take a look at how we can apply some of what we've been talking about with vector valued functions to the quote unquote real world. And specifically, we're going to talk a lot about motion. So this is going to really tie to physics. So for those of you who've taken your physics, a lot of what I talk about physically, you'll completely understand. We're just now kind of bumping it up a notch now that we've got some math tools to help us. For those of you who have not seen physics, don't despair. Don't worry. I will do my best to explain what's going on. And if at any point you're curious, just let me know. ask me the question, and I'll be happy to help you out. All right, so let's just start here. When you have a vector value function r, so we have r of t, what this is giving us is position. So it's giving us the location of an object at a given point in time, right, with that t. Now, what we're going to be interested in the physics world are velocities and accelerations. And so most of you probably know that to get velocity, we get velocity by looking at a derivative. So if you were to differentiate the position function r, you're going to get another vector valued function. And what that function is going to give you are the velocity vectors at any specific time. And remember that velocity, or if you're not familiar with this, velocity is a vector, okay? It's a vector, which means it's not just magnitude that matters, but direction as well, because the direction of the velocity vector will actually tell you about the motion of the particle. If we want the speed, recall that the speed is the absolute value of velocity, or in the context of what we're talking about, it's the magnitude, it's the norm of this. But I'm going to write one more thing here just to kind of tie it into the other way that we can describe the curve. And here the speed is not only the magnitude of the velocity, but you can also look at it as the derivative of the arc length with time, right? Change in arc length with time, change in distance traveled with time. So if we've got the arc length parameter, we can also find it as ds dt. All right, and then of course the next step down is acceleration. And acceleration is the second derivative or of the position, or the derivative of the velocity. And so that's our acceleration vector. Again, it's a vector value function. Given time, you plug in that t. It's going to give you the arrow, but that's going to be the acceleration of that particle. All right, so in terms of the calculus we've done so far, you can do all of this. In fact, you have done all of this in your homeworks. We just may not have actually called it finding the acceleration or finding the speed. Somewhere along the lines, I asked you to find the magnitude of the derivative or something like that. Well, I was actually telling you to find the speed, just not saying that. So in terms of what we're going to do to calculate these things, nothing new. But I do want to talk about acceleration for a bit, because this guy, and I know I've hinted at this as we've kind of gone along, that there are really two portions to the acceleration. Okay, there's what we call tangential acceleration. And for tangential acceleration, I'm going to use a sub t. Okay, so tangential acceleration. And there's also centripetal acceleration, which I'm going to call a sub c. I think this book actually uses a sub n. Let me go look at it real quick. It's really the same thing. It's just going by a different name. Yeah, they use a sub n, probably for normal acceleration, but I usually use c, but I will try to be good and do it just like what the book uses, so that when you go and you look at things, there is no confusion. All right, so we got tangential acceleration and centripetal acceleration. And basically, your acceleration vector is a sum of these two, or you can think of these as two components of the acceleration vector. So we've got A equals AT plus AN. So there's a tangential and a centripetal or normal that add together to give you your acceleration, your complete acceleration. All right, now the reason we break it down into these two, at least from the physics perspective, is they do different things. Tangential acceleration, this changes the speed. So if your particle is going through some sort of change in speed, it is experiencing tangential acceleration. If it's got constant speed, there's no tangential acceleration. Okay, so that changes speed. And then the centripetal acceleration, and remember centripetal means centrally pointing. So this is pointing towards the center of that oscillating circle. This changes the direction. So if you have a particle whose direction is not changing, or whose path is not changing, it's going through no centripetal acceleration. And if this particle is such that it's not changing speed nor changing direction, neither of those is happening, then there's no acceleration whatsoever. And for those of you who studied physics, that's good old Newton's first law, right? A body at rest tends to stay at rest, body in motion stays in motion, unless acted on by an external force, blah, 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 right? That's what is going on there. Okay, so our goal is going to be to take accelerations and split them up into the two pieces. Given just any old acceleration, we want to see if we can somehow figure out what portion of it is pointing tangent to the curve and what portion of it is centrally pointing. Now, there are some paths that we know what happens with these. For example, uniform circular motion. If you're just going in a circle at a constant speed, all of the acceleration is the centripetal, so it would all be a sub n. A sub t would be 0. But we want to expand this to any old kind of path, right? Given any r of t, how can we find the a sub n's and the a sub t's? Okay, well, here's what we're going to do first. Let's think of this acceleration as something times the unit tangent vector plus something else times the unit normal vector. So basically, this is going to be a sub t once we figure out what the magnitude is. And then the other one's going to be a sub n. Right? Because if the tangential acceleration is tangent to the curve, it points in the direction of the unit tangent vector. We just have to figure out how big it is. And then the centripetal pointing one, right, the one that's pointing towards the center of the circle, that's going to be pointing in the direction of n. And again, we just need to figure out what magnitude it has. Okay, so that's our goal here. Let's see if we can figure out how big those components are. Well, we're going to actually start with just good old a is the derivative of the velocity. All right, so we're just going to come back up here where acceleration is the derivative of velocity, velocity is derivative of position, and let's use that to figure out what those things look like. Okay, so let's just start here. A is equal to v prime. But v, we know something about that. It's r prime. Now, what I'm going to do is I'm actually going to introduce big T. I'm going to get big T in here using what we know about big T. By definition, big T, that was equal to r prime divided by the magnitude of r prime. So if I just rearrange this, I get that r prime is equal to T times the magnitude of r prime. So let's just fire this into here. So now we know that our velocity, it's actually the same as t times the magnitude of r prime. And now let's differentiate that. Let's differentiate this with respect to time. So this is going to be our acceleration. And then on the other side, we have to do the product rule. All right. So with the product rule, we're going to get t prime dotted with the magnitude of r prime. So the derivative of the first one times the second. And then we're going to get plus the derivative of the second times t. So this is going to be, I'm just going to write this right now as d dt of the magnitude of r prime times big T. All right, so far so good. Now check this out. We're starting to get what we want. Remember we wanted something times big T? Well, we now have that, right? We've got something times big T. But we also wanted something times big N. And we don't have that yet, but we're going to do the exact same trick. Remember the trick that we pulled up here with that big T? We introduced it using its definition. Well, we can do the same thing with big N. We know that big N, that's T prime divided by the magnitude of T prime. Well, you notice over here we've got a T prime. Let's do exactly the same thing. Fire this in here. So what we now have, I'm going to rewrite it just so that it's more in the order of what we had up here. Something times t plus something times n. So our acceleration, this is going to be d dt of the magnitude of r prime times big T plus, now if I replace this stuff in, I'm going to get the magnitude of r prime times the magnitude of t prime times big N. Right, when I solve this thing for t prime, that magnitude pops up, and we're here. All right, so in essence, I'm done. We're going to go a little bit further because we can clean this up a little bit. But what we've ended up having now is this multiplier on t plus multiplier on n, and those are going to be the components of our acceleration vectors, the part that's tangential and the part that's directional. Okay, well, let me just do one more thing to kind of pretty this up a little bit. If you go back to curvature, one of the forms for curvature, because remember we had like 4 of them, one of the forms for curvature was the magnitude of t prime divided by the magnitude of r prime. I think that was number 2 on our list, but we definitely had this. So what I'm going to do is I'm actually going to use this to replace our magnitude of t prime. So I can throw that in here. And what we end up with then is a d dt magnitude of r prime. So that's that piece. And then this other piece is going to be curvature times the magnitude of r prime squared times n. And this is the magnitude of r squared because there was the one that was already in there and the other one that's coming from our replacing of the big T. Okay, so now this is one of the times that I get kind of excited because when I teach physics, and I'm sure the same thing happened to you if you had Kathy teach you physics or whoever it was, and you're talking about accelerations, and I kind of just made that statement of tangential acceleration changes speed, normal acceleration changes path, right? And you guys all just sort of go, okay, right? You do the old smile and nod, and they'll, well, obviously Bruce knows what he's talking about, so why would he lie? Right? Well, here's what's beautiful. Now you can see it. This shows us why, right? Because check out the tangential piece, right? The tangential piece, its magnitude is from the change in the magnitude of r prime. Well, this is the change in speed, right? The magnitude of r prime is the change in speed. So just from the math alone, that's the change in speed. So tangential acceleration changes your speed. Okay, if you look at the other part, the normal part. All right, so this second one, this is just your speed, right? So it is what it is. It's not changed. It's just your speed. So you get your speed squared, yay, whatever. But notice that what this affects is k. This changes curvature. Well, if you're going to change your curvature, you're changing your path. So it's really beautiful. The math tells us exactly what we see experimentally, right? And this is one of the reasons why I really love physics. I see the interconnectedness between these things, and I love the fact that we can start with just, like, think about how we built T and N and everything, just straight from the math. We just use the rules of math, we build this. And yet it magically describes exactly what we see when we do the physics. So to me, this is just like, this brings tear to the eye, right? It's that beautiful. So thanks, Victor, for that. I appreciate that I get a little cool out of you too. All right, so cool. Yeah, I think it is cool. But still, this is not terribly useful. I mean, it's difficult to do, right? I mean, the first part's not terrible. We can find the speed pretty easily and then differentiate with respect to t. That's not so bad. The other one, though, requires finding curvature, and curvature is a challenge. So what we'd really like is another way of representing these components, or another way of getting to those components. And it turns out that there are some really easy ways of getting those magnitudes. So let me, I'm going to head back up here, erase all this stuff we used to kind of derive it so far. Okay, but I'm going to try to leave this just for right now. Okay, so let's look at this tangential piece. Well, if we want to figure out this component, so the magnitude of the tangential, what we're really looking for, or actually, no, better way, I don't want this as the magnitude. We're just looking for this tangential piece. Think about what we want to do. We're trying to find the projection of this A in the direction of T. So hopefully you remember from last quarter, when you learned a little bit about vectors, that when we want to find the projection, we just do that dot product, right? So what we're going to do is we're going to take A and we're going to dot it with t. And this is going to get us the projection in the direction of t. Okay, well, let's look at what t is. T was the derivative of r, so v, divided by the magnitude of v. And so that's what we're actually going to put in as our component here. At a, it's actually just going to be v dotted with a over the magnitude of v. So your tangential component has this magnitude.
I was wondering when it was going to get easier.
Yeah, because like I said, this is super ugly looking, but you can imagine how fast this is going to be. If we're given an r, we differentiate, find v, differentiate again, get an a, quick dot product, boom. Okay. Really, the reason I went through this derivation was to show you that it is change in speed versus change in curvature. But now we're going to get to the functional, how we do this. Okay, so for the n, we're going to do exactly the same thing, except we're going to take a and we're going to dot it with n. All right, so we could do a similar approach where we take the definition of n as a t prime over the magnitude t prime, but I really don't want that. What I'd rather do is look at it just in terms of like a and v, right? I don't want any of this middle ground stuff. If I can get away from finding t, if I can get away from finding n, I really want to. Okay, so instead, let's think about it this way. Let me show you geometrically. So again, we got some curve. We've got our t and we've got our n. And then somewhere in here is our acceleration. So let's just say that this is a for the sake of having something. Okay, so that's the acceleration of our particle at this point. But I want to find the components in these two directions. So to get the one with t, if I look at the angle in between them, this is a cosine. And so that cosine comes from the dot product. If I look at the angle with respect to n, it's actually the sine, because the n would similarly be up in here, right? And so it's the other angle here. If I just move n, let me just move n here, so n is down like that, right? Now I'm looking at that angle. So instead of needing this, the cosine of this angle, I need the sine of that angle. Okay, well, if I do that, to get the sine, I need to use the cross product. So it turns out that this one is the magnitude of v cross a divided by the magnitude of v. And this is found really just by using a little bit of geometry. Okay, so I'm going to put that in as my component over here. But again, it all comes back to knowing just v and a. But I know what you're thinking at this point. Crap, I gotta do a cross product, and then I gotta find the magnitude. No, let's be smart about it. Let's actually come back to this picture. All right, so let me unmuddy it a little bit. I'm gonna take away the curve, okay? But we're gonna have some v, or sorry, some t. We'll have an n. I'll move it this way just for the sake of having it. And then I'm going to have my acceleration. Okay, so like here's our picture. So think about what we're doing. We're breaking this into components so that we've got one component that points in the direction of t, and another one that points in the direction of n. So here's my AT and my AN. Well, what I know is that A is equal to AT plus AN, right? So if I want like magnitudes, the magnitude of A when squared is going to be the sum of these two magnitudes squared from good old Pythagorean theorem. So if I actually want to get A sub n, its magnitude, it's going to be the square root of the tangential acceleration, the magnitude of AT squared, minus, or whoops, regular acceleration, sorry, minus the tangential acceleration squared. And this is really how you're going to do it, right? Because you'll know the magnitude of the acceleration, easy peasy. You're going to find the magnitude of the tangential acceleration using this thing. And once you know both of those, you can just use the Pythagorean theorem. So practically, this is how we're going to find that magnitude on the n. Even though you could take a cross product and go through that. The other reason I like to show this is look at the symmetry here. Look at how similar these are. The one is a dot product, the other is a cross product, but otherwise they have the same structure. And that's just because of the geometry of space. So take it for what it is.
So I have a question.
Yeah, go for it,
So
brother.
in your full A, is that T and the N placeholders at this point? Or are we multiplying
No,
those?
this is like I and J.
Cool.
Right? Like, you know, when we write vectors as 3i plus 4j,
Yeah. Mm-hmm.
right? It's telling us to go 3 in the I direction and 4 in the j direction.
Yeah.
That's what these are doing. This is saying move v dot a over the magnitude of v in the direction of the tangent. Move whatever distance this is in the direction of n.
Okay,
so those t and n have to be there because they're basically telling us which direction those things are going. Because remember, vectors have a magnitude and a direction. And while it's the magnitude that usually matters in the physical world when we're trying to actually do calculations, the direction is necessary if they're going to be vectors. All right. So, other questions? All right, well, let's do an example. Let me real quick, though, write this last little thing with the Pythagorean theorem back on this side, because otherwise I will erase it, and then we're going to be bummed that we don't have it. I'll try to write it down under the glare. So the magnitude of a sub n equal to the magnitude of a pi squared minus the magnitude of at squared. And just remember that this is an alternative to that. Okay, you can use them either way. All right, so let's visit a path and let's talk about accelerations and velocities and speeds and whatnot. And so we're going to go to our good friend, the one we always seem to do when we start off here is, how about we look at cosine t, sine t, t. So that's the helix, just the standard helix. But let's find velocity, let's find speed, let's find acceleration, let's break the acceleration into the two pieces, so on and so forth. All right, so there's r, let's get r prime. And I think I'm going to stop drawing arrows just because A, I'm lazy, B, I think it gets things a little bit more confusing, and C, we know that these are all vectors. So there's R prime. So R double prime is minus cosine minus sine 0. So in terms of the language of physics, right, this is our velocity, and this is our acceleration. All right, so the speed, it's the magnitude of R prime. So it's the square root of sine squared plus cosine squared plus 1, which is the square root of 2. So it turns out the speed of this particle is not dependent on time. It's got a constant speed, but it does not have constant velocity. All right, now that actually just told me something, and I don't know if you guys caught it. Since the speed is constant, you know something about the acceleration stuff.
0, yeah.
Okay, what's 0? Which one?
Position.
Yeah, thanks, Victor. The AT.
A sub the n.
It's going to be the AT. The AT should be 0 because it's the tangential that changes speed. The normal changes direction. So what we should find from this is that A sub t is equal to 0. So all of our acceleration should be normally pointing. But let's see that. Let's actually show that that must be the case by looking at these two components. All right, so let's get them. So if we're going to do V dotted with A, V dotted with A is going to be minus sine times minus cosine plus cosine times minus sine plus 1 times 0. So this is a sine cosine, a minus sine cosine, plus 0, which is 0. So the magnitude of V doesn't actually matter. And so we do see then that AT is equal to 0. So in a situation like this, if you ever get to a point where your speed is constant, save yourself some time and just jump straight to, oh, okay, AT, that's 0. So all the acceleration points in the normal direction. Okay, so we could, if we wanted to, now go and calculate what the magnitude is in the normal direction. But I'm not going to use this formula. I'm going to be smart about it again. We know that all of the acceleration is normal because AT is 0. So the component that's normal is A. So if I just divide by its magnitude, or whatever its magnitude is going to be this thing. And the result is going to be n. So this is even better in this situation since we have constant speed, because now I can figure out where n is without actually having to go through finding t, doing the t prime over the magnitude of t prime and all that. So check this out. We've got our acceleration right here. Let's get its magnitude. So the magnitude of acceleration is the square root of cosine squared plus sine squared plus 0 squared which is 1. So for this guy, the acceleration on this helix is 0 times t plus 1 times n. So even better, not only is this last vector a, it's also n. Kind of nice. I don't know if you remember, we did find n for this thing. Go back in your notes and look at it, where we found big T, and then we went through the process of differentiating it and dividing by the magnitude. And we ended up with n being minus cosine minus sine 0. But this actually brought us there much faster.
We sure did.
Yep.
It's crazy.
So that's one of those things where the brute force method isn't necessarily the one you want to do. And so it's helpful to be paying attention to things as you go. Like when we did this before, we found the square root of 2 for the magnitude of r prime, right? We had to in order to find t. But as soon as that hit, and this is where I have the advantage of having done calculus for decades on you. As soon as that hit, I went, ooh, I know all kinds of great stuff. Now I know that my normal vector is going to be pointing in the direction of my second derivative, my acceleration. And so when we got to our acceleration, I just looked at it and went, oh, that's magnitude 1, that is n. But I was looking for it. Now you guys can start looking for it. All right, so watch for that constant speed. If speed is constant, oh my God, that's so awesome. Because you're going to be able to find n fast, super fast. All right, so there's an example with the helix, but you probably feel a little cheated because we didn't really have to do any work over here to find it. So let's do another one. We'll do another function, vector value function. We'll do the same thing, but this time we'll specify at a t value where we want to calculate all this stuff. All right, so let's just say r is equal to t squared minus 2t, comma, t plus 1, comma, square root of t. All right, so it does whatever it does. And I want to find v speed a, t, an, like I want to find all this stuff at t equals 1. All right, so let's do it. So v, it's r prime, which is going to be 2t minus 2, 1, 1/2 t to the minus 1/2. Let's go ahead and figure out what this is at 1. So v of 1 is going to be 0, 1, 1/2. So speed, and we'll just go ahead and do it right now since we want the speed at 1, is going to be the square root of 0 squared plus 1 squared plus 1/2 squared, which I believe is root 5 over 2. So we'll put little check marks next to the things that we've already calculated, speed. Now, be careful. I know how last time I said, hey, if speed is constant, we know a lot. This speed isn't necessarily constant. This is the speed at a point. It best be that we just get a number when we find the speed at a specific point in time. But this doesn't mean that all of the acceleration is normally pointing. Because we didn't actually find the speed of this thing. And if we find the speed of this, I'm going to probably, I'd be very willing to say is not going to be constant. But we'll find that out as we move to the next stage. All right, so there's our V. Let's get A. We'll go ahead and box the things that we were looking for. Let's get A. So A, the derivative of V, so R double prime, is going to be 2, 0, minus 1/4 t to the minus 3/2. So the acceleration at 1 is going to be the vector 2, 0, minus 1/4. All right, so now let's figure out what portion of this acceleration points in the direction of big T and what portion points in the direction of big N. All right, well, now we're going to go to this formula right here. So let's do V dotted with A. If I do that here, we should be able to see it, right? Yeah, no glare. All right, so V dotted with A, it turns out that I can go straight to the V and A that we calculated by plugging in 1. I don't have to go back to the originals. So if I take those two and I dot them, I get 0 times 2 plus 1 times 0 plus 1/2 times minus 1/4, which is negative 1/8. So the acceleration is actually pointing in the opposite direction of t. It's going backwards a bit. We'll talk about what that means physically here in a second. So v times a, v dot with a is minus 1/8, but then I need to divide by the magnitude of v. So the magnitude of a sub t is minus 1/8 divided by root 5 over 2, which is negative 1 over 4 root 5. All right, so that's that component. Let me kind of rewrite what or kind of go to where I'm heading here. I'm going to have my A equals, I now have negative 1 over 4 root 5 times big T. And then we're going to have something times big N. All right, so remember when I was talking about how this speed is probably not constant? We know that's the case because there is tangential acceleration. All right, so now let's get the normal piece. Well, let's use the Pythagorean theorem. So we know the magnitude of A at this point. That's the square root of 4 plus 0 plus 1/16. So that's going to be root 65 over 4, because you end up with 65/16. We also have the magnitude of a sub n, right? That's already written there. So the magnitude of, or sorry, a sub t, the magnitude of a sub n then is going to equal the square root of this thing squared, 65/16, minus this thing squared. 16 times 5 is 80. So I think that should be minus 1 over 80. He says very uncomfortably. So if that's correct, 325 minus 1 is 324. So this is the square root of 324/16, which is the square root of 81/4, which is 9/2. No way. Sweet. That worked out a lot nicer than I thought it was going to. All right, so then that leaves us with plus 9/2 times n. So there is a tangential piece, there is a normal piece, and so what's happening with this particle is it's changing direction and it's changing speed. I could also use this to help me find n, because remember how finding n can be a challenge? I can find t really easily. Since I've got the velocity vector, I just have to divide by its magnitude, and that'll get me my t, right? So like if I just look right here, t, big T, is going to be this velocity divided by its magnitude. So that's going to be 0, 2 over root 5, 1 over root 5. So that's the direction that the tangent vector points. I could then use that, plug that in up here for t, multiply by the minus 1 over 4 root 5, subtract that off from the a that I know, then multiply by 2/9, and that'll get me my n. And I know there are a lot of steps there, but each of those steps is way easier than doing the horrible derivatives that we have to do to find n. Okay, so this is the general process, and it doesn't matter what kind of particle or what kind of path it's taking or anything. You can always figure out all of this using just some simple math. I mean, it may not feel simple, but it is simple stuff, right? Dot products, Pythagorean theorem. That's pretty much all we did here when it came time to actually calculate those numbers. All right, well, anyway. So one last thing I want to mention about this guy, just for you physics types. This one's actually slowing down because the tangential acceleration was negative. This one, whether it's plus or minus, will tell you about the speed, what's going on with the speed. If it's positive, it's speeding up. If it's negative, it's slowing down. The plus or minus on the n, what it does tell you is it getting more curvy or less curvy? But the problem is it could be getting more curvy even if it's negative, if we kind of were on the negative side of things already. Right, so that one's a little bit harder to see just right away, but just realize the sign of the magnitude of t here, or the magnitude at, that sucker will just tell you whether it's speeding up or slowing down. All right, so a little bit more of a complicated path led to a little more challenge in terms of finding these things, but it's a really pretty simple process. So yeah, I was going to say let's do another example, but we're like 5 minutes from the end of class anyway, so we're going to go ahead and call it now. What I was going to show you next was projectile motion and kind of how this stuff falls into there. Let's say that for Monday. As such, this homework section was supposed to be due Monday at midnight. I'm going to move that to the following week. So I'll try to remember to do that as soon as we're done with class. If I don't remember to do it by Monday, remind me that I said that this section would be moved. It's section
3.4.
3.4. Okay, so 3.4 will actually be due a week from Monday, not in 3 days. Okay, because I want to talk a little bit more about it. Anyway, so hopefully this today gave you a little bit of a, oh, now I see why we care about this. At least for those of you who've taken physics. For those of you who have not taken physics, take some damn physics. It's pretty cool. And then I'll tell you what, if you haven't taken physics yet, now you're going to be totally equipped that when you dive in, your professor's going to be like, whoa, what are you doing? Let's slow roll. But you go, no, I know that this is a better way. So anyway, there was a reason calculus was invented. It was to be the language of physics. Just turned out that it was really useful in lots of other places.
I have a question.
All right. Yeah, go for it.
So I'm sure we're not ready for this, but what if you wanted to take gravity into consideration with something like this? Like something falling.
When on Monday, we'll do that, at least small scale, we'll do the good old gravity is constant kind of thing, talk about on Earth, what you would do there. But let's just say like that this is the path of some particle, some spacecraft, right? And we do want to take into account gravitational attraction to the sun, Earth, Jupiter, all the bodies. That's definitely done, except you would go backwards, right? You'd use Newton's second law, good old F equals ma. You'd look at the sum of all the gravitational forces so that you would get a force vector, divide out by the mass of the object so you get the acceleration vector. Then you would integrate to get velocity, integrate again to get position, use some initial conditions because you would know, okay, well, we're launching it from Earth so that it has this speed and, blah, blah, blah. And then actually, now you've got your R vector. So it's kind of the other way around, but yeah, no, absolutely. You take all forces into account to then build your position function. And that's what we'll do next time when we talk about like projectile motion. We'll start with acceleration, work our way back to position vector, and along the way talk about all these other things that we're seeing.
That's so crazy.
I know, right? You have so many tools now.
That's fucking crazy.
And that's why when people tell me, when someone will go like, oh, that's not hard, it's not like it's rocket science, my initial reaction always is like, oh, rocket science isn't hard. And they look at me like I'm, a freak. I mean, that's fair, right? But then I'm like, no, it really isn't. It really isn't, because there are just a couple of laws that govern what goes on. And all you got to do is put it together and then do some math on it. But this is coming from someone who is not concerned about doing the math on it, who doesn't have trouble putting all of those forces together to get accelerations and all that, right? So I understand why, to someone out there, rocket science is difficult. But I mean, you guys are ready. Legit, you guys are ready to do this. You've got the tools you need. So think about how awesome that is, right? All right, anything else before we call it a day? All right, well, then I'm gonna go ahead and pause the recording, but again, have an awesome weekend, and I will see everybody on Monday.
Thanks, Bruce. See you then.